Beams are the most frequently used superstructure systems in bridges. While less efficient than trusses or arches, they are very space efficient. We see them in short, simple spans in major road systems and as subcomponents in virtually every bridge. Engineers call large beams and beams that support smaller beams girders. In this video, you will learn why structural steel is frequently chosen for bridges, how to configure beams, find their internal forces, and how to size a beam while considering stability challenges. The steps in beam design are 1. Material selection, 2. Bridge configuration, 3. Structural analysis, 4. Stability bracing, and 5. Beam sizing. The original Van Buren Bridge was built of ASTM A7 steel, which was extensively used during this era. It has an ultimate strength of 55 KSI and specified yield strength of half that. New bridge steels today follow the requirements of ASTM A709, also known as AASHTO M270. This comes in various grades with yield strengths ranging from 36 to 100 KSI. AASHTO currently recommends using high-performance steels abbreviated as HPS. These are weathering steels with improved welding, corrosion, and fracture toughness characteristics. A next step in bridge design is to determine its structural configuration. This will be a function of configuration of what is being crossed, roadway alignment, clearances, spans, often driven by substructure options, number of lanes and pedestrian access, redundancy. The Steel Bridge Design Handbook, published by the National Steel Bridge Alliance, has excellent chapters on bridge type selection and stringer bridge configuration. With the bridge configuration, an engineer can then develop how the beams are laid out in plan view, known as the framing plan. For the new Van Buren Bridge, the designer placed 2 bents in the river and 1 on each bank. 5 3-span girders run between these, creating a primary superstructure. These girders are hunched and at their deepest point sit on bents 3 and 4. 3 methods of beam analysis are common today: beam formulas, shear and moment diagrams, and finite element analysis. We will discuss the first 2 in this module and finite elements in Module 6. For simple beam loading, a wide variety of formulas exist that provide shear, moment, and deflection at any point along the beam. For linear elastic analyses, we can superimpose these beam solutions for combined loading. This can provide a nice check on software. Shear and moment diagrams plot the load, shear, and moment along the length of the beam. We can solve any statically determinate beam this way. Let's look at the beam that ties the 2 trusses together on the Van Buren Bridge. While the primary spans of the historic Van Buren Bridge are trusses, 3 beam-type framing members carry load from the vehicle wheels to the trusses. The timber deck, acting as a short beam, holds up the vehicles. The deck is supported by 19-foot timber stringers. These deliver their load to the steel floor beams, which are supported by the truss verticals. Focusing on the steel floor beam, we see how the dead load, 640 pound per foot lane and truck load, arrive on the beam. Because the stringers are closely spaced, we apply their force as a line load. We can then draw its free body diagram and are now ready to analyze the beam. We have 2 magnitudes of line load and 2 point loads. This represents the factored loading on the beam. We now solve for the reactions using 3 equations of equilibrium. To do this, we first condense the distributed load into point loads. Summing moments about the left support, we develop the following relationship. Solving for the right-hand reaction, we get just over 101 kips. Following this approach, we can next sum moments about the right reaction and find that the left reaction is 60.4 kips. Summing forces vertically, we see they equal 0, giving us a check on our math. With the loads and reactions, we now have a complete free body diagram and can now draw the shear diagram. We do this by moving from left to right or right to left. When we cross a load, we apply its effect on the shear diagram. In mathematical form, the change in shear is given by these equations. Starting on the left, we cross the left reaction, which creates a positive shear of 60.4 kip. The line load W sub U sub 1 creates a change in shear equal to 2.26 kip per foot. We subtract this from the reaction shear. Going 9 feet, this creates a negative 20.34 kip change in shear. Subtracting this from the left reaction, the shear is at this point a 40.06 kips. For the next 2 feet, we repeat this with the larger line load W sub U2, generating a change in shear of negative 9.62 kips and resulting shear magnitude of 30.44 kips. Arriving next at the first point load from the truck, we see an instantaneous change in shear of negative 44.7 kips. This takes the diagram downward to negative 14.26 kips. The line load continues to cause a negative change in shear of negative 28.86 kips, yielding a shear magnitude of negative 43.12. Coming to the second point load, the shear changes instantaneously to negative 87.82 kips. Calculating the change in shear from the 2 remaining line loads, we get a resulting shear of negative 101.2 as we arrive at the support. Subtracting this shear from the reaction, we get 0, thereby closing the diagram. If it doesn't close, it means we made a mistake and we need to check our work. Combining these steps, the final shear diagram looks like this. It's important to note that we can go from right to left in creating the shear diagram. We then get a diagram that is mirrored about the horizontal. Because shear creates an equal and opposite effect, this is equally valid. To create the moment diagram, we find the change in moment as the area of a discrete portion of the shear diagram and add any point moments applied on the beam. Mathematically, this can be expressed as these equations. Because this beam is simply supported, it has no moment resistance at the end. Going 9 feet over to where the shear diagram changes slope, we find the area of this portion as... This gives us our first moment on the diagram. If we are unsure of the shape up to this point, we can choose a smaller distance and find intermediate moments to generate the curve. Going from the 9-foot to 11-foot mark, we find the area under the shear diagram as... Adding this to the moment at 9 feet, we get 522.6 kip feet. The point where the shear diagram changes from positive to negative marks the maximum moment in this case. To find the change in moment for the next 3 points, we find the areas under the shear diagram as 172.1, 185.3, and 165.9 kip feet, respectively. This gives us moments of 350.5, 165.2, and 0, respectively. Note, using these numbers, there is a negligible rounding error of 0.1%. This gives us a completed load, shear, and moment diagram. Using principles of mechanics of materials, let's look at how we select or check a beam based on the AASHTO standard. This requires consideration of beam proportions, shear strength, bending strength, and deflection. Out of necessity, the AASHTO specification is extraordinarily detailed when it comes to flexural design of plate and composite girders. We will focus on the most fundamental flexural strength equations and leave the specification to expand. In order to keep beams performing as anticipated, AASHTO has several member cross-section proportional requirements. These are based on experience, testing, and local buckling calculations. The shear strength V sub n of an unstiffened web is given by this equation, where C is the shear buckling to yield ratio, F sub yw is the web yield strength, and D and T sub w multiply to give the area of the web. The shear buckling to yield ratio depends on the web slenderness ratio D divided by T sub w. When this ratio is less than this equation, C equals 1.0. The AASHTO specification provides equations for C when the web slenderness ratio is larger. Multiplying the nominal shear strength by the shear resistance factor, we get the design shear strength. When this is greater than the factored shear, from either a beam formula or shear and moment diagram, the member is adequate for shear. Flexural resistance, also known as bending moment strength, is influenced by material strength, section modulus, local slenderness, and flange bracing. There are 3 driving regimes in flexural resistance: yielding, local buckling, and lateral torsional buckling. Yielding begins when the bending stresses reach the material's yield stress, and follow basic principles of mechanics of materials. Local buckling occurs in compression regions in slender elements. Lateral torsional buckling happens when the beam rolls over due to internal compressive forces in the member with insufficient bracing. The first limit state for flexural design is yielding of the cross-section. Engineers tend to look at two conditions: initial yield of the cross-section and full plastic yielding. The LRFD methodology is based on plastic yielding. The flexural strength of a yielding beam is given by this equation. The Webb plastification factor is the ratio of the plastic moment, m sub p, to the yield moment m sub y. In their most simple form, for a non-composite beam, m sub p equals the plastic section modules times the yield strength, and m sub y equals the elastic section modulus times the same. When flexural members are not symmetric about the horizontal axis, we consider the tension and compression areas independently and use subscripts of T and C to denote this in the equations. Local buckling occurs when compressive forces in slender elements overcome the stability of the member. When the compression flange slenderness ratio is below the following relationship, local buckling won't occur. If it is larger, the nominal flexural resistance of the member is given by this equation.
So lateral torsional buckling happens with I-beams. An I-beam is really good if it's loaded as it was designed to be loaded. So like on a steel girder, it's designed to carry the load in the vertical axis. And as long as it's vertical, it's going to operate just like it was designed. But if you take an I-beam and it's just by itself, it's going to get squirrely. Even picking up an I-beam, it's got specific pick points. If you pick it up at the ends, chances are it's just going to bend right in the middle. So every stage of construction with a girder, it's critical to analyze lateral torsional buckling. And then once it gets in place, it's got to be braced. Lateral torsional buckling is a problem because if it's not braced, you never give the beam a chance to perform as was designed. Okay, so bracing for lateral torsional buckling, if your top flange is embedded in concrete, that'll be braced. It's not going anywhere. But the bottom flange needs to get braced, and if you just use some small angles from the top to the bottom, make a big X out of it, that's one type of brace that can be used. You can also use what's called a diaphragm, which is more of just a large piece of steel between the girders.
Lateral torsional buckling occurs over two regimes: inelastic and elastic. When the brace spacing L sub B is between L sub P and L sub R, we use the following equation to determine the flexural resistance of the beam. This is a function of the moment gradient factor, section modulus, Webb plastification factor, yield moment, brace spacing, and cutoff lengths for inelastic and elastic behavior. This equation can be overwhelming at first glance, but taking one term at a time, we can work our way through it. The limiting unbraced length for nominal flexural resistance L sub P is given by this equation. It is a function of the effective radius of gyration, modulus of elasticity, and flange yield strength. The limiting unbraced length to achieve the onset yielding L sub R is given by this equation. It is a function of the effective radius of gyration, torsional parameter, section modulus, distance between flanges, yield strength, and elastic modulus. When the brace spacing L sub B is greater than L sub R, we use this equation to determine the flexural resistance of the beam. This is a function of the moment gradient factor, section modulus, brace spacing, effective radius of gyration, torsional parameter, distance between flanges, and elastic modulus. Looking again at flexural strength versus brace spacing, we see that as the unbraced length L sub B increases, flexural resistance decreases. Multiplying the nominal flexural resistance by the strength reduction factor phi, we can now compare this to the moment in our beam. AASHTO provides optional deflection criteria. The first part of this table provides these criteria for different load and member types. The The second portion shows the allowable deflection for varying spans. Engineers use the live load portion of the service one load combination. In this module, we have introduced bridge steel types, highlighted resources on how to configure girder bridges, learned how to calculate beam, shear, and moment formulas and diagrams, and how to check their strength. While this is just the tip of the iceberg, with this knowledge, you now have the fundamental tools with which to design beams.